Hello, my name is Jill Wang, and I did P3, which is the link strand DNA enzyme splicing and replacing um, project. Okay, so the DNA project kind of, as I said, models enzyme splice and then replacement of like a DNA strand in Java. So it'll take like a long string of characters that's supposed to represent a DNA strand with all the little characters that represent each DNA building block. And we have created a bunch of strand, iDNA strand um, implementations of this interface so that we are able to um, splice and replace enzymes or model that in Java. Okay, so the append method. The append method for uh, my link strand class is just creating a new links node with the info. That's our parameter, DNA, and the next um, node that this current node was pointing to is null. And then we're setting our instance variable myLast, the next equal to this current, because this is the new class node. MyLast is equal to current, and my size plus equals DNA.length. So just the length of the string, it will be added to the size of the whole link strand. And then my appends plus plus because we appended one time. And then we'll return this object, this node. Okay, well not this node, sorry. The the head that this node is now part of, we're going to be returning that. So our entire DNA strand. The time complexity of the link strand append method is O of 1. This is O of 1, which is creating a node, O of 1, setting stuff equal, and then plus plus is O of 1 and return is O of 1. So the entirety of this append method is O of 1, whereas in string builder, strand append is O of n, because we're the append in string builder is O of n, and in string strand it's even more inefficient. It is O of n squared, because that's what happens when you concatenate strings in Java. Okay, the test cases that were most helpful for this was definitely, I'll run a test case right now. The best test case was for sure, sorry, let's run test strand. It would definitely be test append because we're testing the append method in here. And so, yeah, that's how the append method works in link strand. So the next method we'll be going over is actually in, it is in GAR DNA alternator, I think. No, sorry, it's an iDNA strand, and it's the cut and splice method. So the cut and splice method basically does the real, I guess like dirty work of cutting and splice, like finding a string of letters in your strand, like deleting it and then replacing it with a new string, which is called a splicey. Okay, so the cut and splice method. This is setting a bunch of variables at the beginning, and then basically while um while we still have another instance of the enzyme from the start of where we're splicing from, then we're gonna obviously keep splicing. And then when we run out of enzyme occurrences, this will return -1, and then so it'll be less than 0, and then we will cut out of the while loop. So we have a different implementation of the first enzyme encounter. So if it's the first enzyme encounter, then we're gonna get this instance. We're gonna search a substring, start to finish, and then we're gonna set the first Boolean to be false. And otherwise, if it's not the first instance of the enzyme, we're just gonna find and replace the enzyme with the splicey. Okay, and then that's the whole problem. So in here, we're just adding on the enzyme length every single time we go through so that we so that we know to start at a different length. And then we're just appending the splicey. And yes, this is just if the enzyme is never found, return an empty string. So I'm just gonna return an empty string here. And then we return our new string with the enzyme replaced by all the splices. So the conclusion to this project was I found that this project was really about comparative runtimes. So linked lists are more efficient when you need to just keep when you don't need to find stuff at a specific, I guess, like index. And so the trade-off for that is that linked lists in this case are easier to make an iDNA out of, and the runtime is better for a specific case.